Hi, my name is Srihari Vishnu, and this is my ECE 106 design project where I built a capacitive sensor to report the level of moisture within a clothing item. Description of sensing application. The sensor is designed to report the moisture content left in a clothing item and alert the user when the clothing is dry. This can be used, for example, on a clothing line, and the sensor is attached to a clothesbin so that it is in direct contact with the clothing item. While drying, the sensor outputs the moisture content left in the clothing item, and when it's done, when the clothing is dry, it alerts the user. To build the sensor, I used an Arduino, a clothespin, cardboard, and aluminum foil. The geometry of the sensor is that of a parallel plate capacitor, with the aluminum foil as conductive plates attached to each side of the clothespin, and the clothing material as the dielectric. The dielectric constant of dry cotton is 1.4, while the dielectric constant of water is around 80. This large difference makes it easy to sense when it is dry and when it is wet. The dielectric of the material changes due to water evaporation. As the moisture content of the clothing decreases, the dielectric constant decreases, and thus decreases the capacitance, which in turn increases the voltage across the capacitor. This is a non-linear relationship. The level of the moisture content is indicated by a brightness of an LED for simplicity in this project, but can easily be modified to output numeric values to an LCD screen or report the values back to a user. Here's a diagram of the prototype I built to measure the moisture level content of this clothing item. On the left right here, you can see that this is the parallel plate capacitor with one of the plates shown here. Both the plates are secured using a clothespin, and you can see that in depth on the right side, with the parallel plate on the left being the positive end and the one on the right being the negative end, connected to ground. You can also see in its diagram right here the LED, which indicates to the user when the clothing material is dry. When comparing the theoretical model of the capacitor to the real-life model of the capacitor, there are some considerations that need to be taken into account. First of all, water, which is usually ionized, is conductive, meaning that charges could flow between the plates. To compensate for this, I used a thin sheet of paraffin wax paper as an insulator between the plate and the clothing item to limit charge conduction. Also, in reality, a parallel plate capacitor has fringe fields. In this project, we do not account for them, but a cylindrical design could mitigate the effect on capacitance. Also, usually clothes are a blend of materials, but the material that I am testing my capacitive sensor on is pure cotton, 100% cotton. However, in practice, this is not always the case, and beforehand, the sensor would need calibration to calculate the dry dielectric constant before using the sensor on wet clothing. Finally, the plates were sometimes at an angle since the clothespin is only secured on one side. To fix this, I could use another clothespin on both sides to make sure that the plates are parallel. Analysis of capacitance. Before I dive into the analysis of capacitance, I'd like to define a few constants. The first three shown are dielectric constants for the various materials used. First of all is paraffin wax paper. The second is the dielectric constant of clothing, which is going to be dependent on the water concentration. And finally, the dielectric constant of cotton. The last two constants are the thickness of the clothing and paraffin wax paper, respectively. I'd also like to define a term called volumetric concentration of water. This is the quantity that we are interested in measuring, that is, the amount of water in the clothing material. And I define this by the volume of water per the volume of clothing, or the mass of water over the density of water over the volume of clothing. So, assuming a linear distribution of water, we can easily relate the dielectric constant to the volumetric percentage of water in the clothing, as shown in the relationship below. For the analysis of capacitance, here are a couple assumptions. First of all, the water is uniformly distributed throughout the clothing material, which is important for dielectric calculations. Second is that the fringe fields are negligible. Third is that the gaps of air within the clothing are also negligible, and I assume that it is pure cotton. And finally, the plates are perfectly parallel to each other. As seen on the diagram on the right, it becomes evident that we have dielectrics in series, and therefore the following relationship is true, given by the reciprocal of the total capacitance is the reciprocal of the capacitance of the clothing plus the reciprocal of the capacitance of the paraffin wax paper. Using the respective formulas, we can derive an expression for the total capacitance. We then, since the dielectric constant of clothing is dependent on the volumetric concentration of water, we substitute this value in to obtain capacitance in terms of the volumetric concentration of water. The result is plotted on the graph as shown. As the volumetric water concentration increases, it becomes evident that the capacitance also increases, and vice versa. Sensitivity of capacitance. To calculate the sensitivity of capacitance, I first take the derivative of the capacitance with respect to the dielectric constant of clothing. I also take the derivative of the dielectric constant of clothing with respect to the volumetric concentration of water. Combining the two relationships, you can see at the bottom that we obtain that the derivative of capacitance with respect to the volumetric concentration of water in the clothing, or in other words, the sensitivity of our arrangement. From the obtained relationship and plugging in the appropriate values, plotting the relationship obtains the graph on the right. And as you can see, as the volumetric water concentration increases, the sensitivity with respect to capacitance decreases. To optimize the sensitivity, there are a couple possibilities. As you can see, we can first increase the area of the plate. From the sensitivity equation, since the area is in the numerator, increasing the area of the plate will linearly increase the sensitivity of arrangement. And a possible optimization is to increase the area from 0.01 meters squared to 0.02 meters squared. Or we can also change the material of the insulator to increase the dielectric constant. So for example, we could change the paraffin wax paper, which has a dielectric constant of 2.3, to rubber, which has a dielectric constant of 7. To compare the optimized sensitivity versus the current arrangement, we plot both of the relationships on the graph on the right. The optimized is shown in black, and the current arrangement is shown in a dashed purple line. As you can see, the optimized sensitivity has better capacitance range, and it also has a greater slope, indicating optimized sensitivity. Circuit analysis. Before diving into circuit analysis, I'd first like to cover the different ranges that the capacitor could have in terms of its capacitance. For 0% water, by plugging into the equation obtained earlier for capacitance, we get that the value of the capacitor would be around 61 picofarads. However, for 100% water, we get that the value of the capacitance would be around 2.47 nanofarads. However, 100% water isn't feasible, so we'll instead use 95% water, which is the equivalent of 2.4 nanofarads. To measure the unknown capacitance, my first arrangement has a capacitive voltage divider, which features two capacitors connected in series. I also have an Arduino to generate an AC voltage at a frequency of 1000 Hz and peak-to-peak of 5 volts. The Vout is the voltage across the unknown capacitor, and it is read by the Arduino and interpreted, which uses pulse width modulation to adjust the brightness of the LED accordingly. Bright means dry, off means wet. The simulations for that arrangement are shown here. When it's wet, the amplitude of the sine signal of Vout is much less than when it is dry. However, the problem with this arrangement is that there is negative signals. Arduinos cannot handle negative signals. They cannot read it, and they may even be damaged by the presence of negative voltage. Therefore, although this may work for an oscillator or an oscilloscope, it will not be viable for an Arduino. Instead, I decided to use an RC circuit. So we still have the Arduino to generate a frequency of 1000 Hz. However, we also have a DC offset of 2.5 volts. This keeps the voltage in the positive range, and since the DC offset is preserved through a resistor, we still have that DC offset at Vout. Here are the simulation results for this improved arrangement. On the left, we have the wet sine signal. It has a very decreased amplitude compared to the dry signal, which has a very increased amplitude. My prototype has the following circuits configuration. So as you can see, to create that 1.1 megaohm resistance, we have a 1 megaohm resistance connected in series with a 100k ohm resistance. This wire right here is the Vout wire, which is reading the voltage across the capacitor, which, as you can see, this wire leads to. The LED configuration is shown on this side right here. Relating voltage and capacitance. So we know that the impedance of capacitor is given by this expression up here, so then we know the total impedance of the circuit because we just add on the resistance value. Therefore, in phasor domain, we have the following relationship is true since it is just a voltage divider. And since we are only interested in the amplitude of each signal, we have this following relationship where Vc is the voltage, the amplitude of the voltage across the capacitor. To find the sensitivity of the voltage versus capacitance, we can take the derivative of the voltage across the capacitor with respect to capacitance to obtain the following relationship. Overall sensitivity. Given the relationship shown, we have that the derivative of the voltage across the capacitor with respect to the volumetric concentration of water is equal to the derivative of the voltage across the capacitor with respect to capacitance times the derivative of capacitance with respect to the volumetric concentration of water. Since we have both of these derivatives, our overall sensitivity is simply given by the product of the two. The value for C is omitted since it would become a more ugly expression, if you will, but it is shown here as well, just for reference. Therefore, the overall sensitivity is dependent on the value of theta. So we plot the results on the right. As you can see, as we approach 0, the sensitivity increases dramatically. To obtain a more sensible result, we will now look into detection limits. To find the detection limit, all we have to do is first calculate what is the smallest possible voltage that the Arduino can measure. So since the Arduino can measure voltage from 0 to 5 volts, but only in 1023 increments, which is a 10-bit resolution, we have that the minimum voltage it can read is 4.88 times 10 to the negative 3 volts. Using this relationship and the derivative expression obtained before, taking the reciprocal of it, we can obtain an expression for the minimum, or d theta, minimum change in moisture content in the sensor. We plot this value on the right. As you can see, as we approach 0, the absolute value of the detection limit is at a minimum. Therefore, as the material becomes more dry, the sensor is more sensitive to changes in moisture, and thus more accurate. Reasonably, for 5% concentration of water, the sensor can detect changes in concentration within 0.036%. However, for 95% concentration, the sensor can detect changes within 4.43%. Error analysis and voltage source noise. The analog to digital converter on the Arduino has an error of plus or minus 2 least significant bits. Since the Arduino has a resolution of 10 bits, which is 1023 possible numbers, this gives us a 0.4% accuracy. Therefore, the Arduino can read voltages with an accuracy of 2 bits times the 5 volts in 1023 divisions gives us 9.8 millivolts. And this is the source of error for reading in the voltage from the signal. Resistors themselves have an error since they are rated as a 1% tolerance rating. We use pulse width modulation for the output to generate the analog sine wave. As you can see in the diagram below, this means it's either 0 or 5 volts, but the only adjustment is being the time that these voltages are being applied. The delay is the main source of error, but we also have some electrical noise. As you can see on these bottom parts here, it's not perfectly 0 or 5 volts sometimes. And one of the sources of electrical noise would be higher valued resistors, such as the 1 mega ohm resistor in the circuit mentioned previously. This electrical noise will create variations and introduce error in the voltage produced and read by the Arduino. We account for this error within the Arduino code, shown later on. Demo. So this first part of the Arduino code is focused on just declaring the different constants, for example, setting up the constants for the sine wave and other things that are needed throughout the program. Here we get into more of the main loop. This is the function generator, so that's going to generate the sine wave for us. And here we get the sensor value from the analog in, which is going to tell us the voltage across the capacitor. The next portion is focused on dealing with that electrical noise and making sure that we get the right range of values within the last 1,000 cycles to make sure we have the most accurate range possible. So we look at the minimum and maximum and make sure that the sensor updates accordingly as time goes on. And this last part is for debugging and writing the output to the LED, as you can see from below here. When putting the sensor on a t-shirt, we have the following waveforms. So when it's wet, we have the waveform on top. We see that the amplitude of the signal is very low. But on the bottom, we see that the amplitude of the signal is very high when it's dry. And that's when we turn on the LED to full brightness. I'll now be playing the demo video of the prototype in action. Okay, so as you can see, I have separated my t-shirt into two sections, a dry section and a wet section. This is the top plate of my sensor, and the bottom plate is under the t-shirt right here. So what I'm going to do is I'm going to put my sensor on and then fasten it with this clothespin. As you can see, the LED turned off and the waveform is very small. Okay, so now I'm going to transition to a drying cloth by moving this sensor to the dry region. So what I'm going to do is remove that, flip over my t-shirt to this side. Okay, sure it's nice and good. Put the plate on it and fasten it with that. As you can see, the LED is very bright and the waveform is very large. For a more specific measurement, we can also look at the serial monitor, and you can see that the difference is around 4.2 volts when it's dry. So here are my references for this design project. Thank you very much for listening to my presentation.